So we shall start the chapter 3 from the Harun al-Rashid book, and I hope the 4th edition is available to you. Is it available? If you don't have, then I'll send it to your parcel. Okay.
Sir,
Hello?
it is better if you send it, sir.
Okay, I'll do that thing. So after the end of this chapter, we should be able to tell or do this thing. So we'll be able to do the classification of the diode rectifiers, and we'll have to figure out then what are the advantages and disadvantages of those different types of rectifier. And we'll be able to explain the operation and characteristics of the diode rectifier, and we'll be able to find out what will be the performance characteristics of performance. I should say performance, not performance characteristics, other than performance parameters of the diode rectifiers, and then we will be able to analyze the and design the rectifiers. Okay. So I hope it has been recorded already. And then,
Sir,
yes.
Sir, sorry for interrupting, sir. In the next week, sir, we have a quiz, inshallah, right, sir?
On Thursday, yes.
Yes, sir. Sir, if you would kindly actually tell us the quiz syllabus and like.
I have already told the CR today's syllabus. Today's class will be the last topics of your quiz.
Sir, from the first of the semester.
Yes, from the beginning. So chapter 1 we have covered from Mohan. Chapter 2 we have covered the reverse recovery characteristics from Harun al-Rashid. And this one I am covering maybe 30% of this chapter. I shall cover today. Okay.
Okay, sir. Sir, if you would kindly, sir, give us some suggestion, sir.
Suggestion is the basic thing you have to understand. Like what is if a transistor works in the saturation and cutoff mode, where it will be operating in the linear electrons or power electrons. So this four option will be there. You have to answer this. You understand?
Yes, sir. So the quiz time and like the details.
I don't know. Maybe 20% and 15 minutes.
Sir, MCQ.
MCQ, of course. MCQ.
Okay, sir.
Google sheet from the Google. We will have to answer from Google sheet. Okay.
Okay, sir. Inshallah.
Sir.
Yes.
Only theory or math problems will be there. I mean for the quiz.
Yes.
It's going to be both theory and math problems.
I didn't understand. What theory? Yeah, there will be theory, and also you have to solve some math quickly, very quickly. Okay, like there will be, it will not take more than 10 or 15 seconds to find out the using your calculator. Okay.
Okay, sir.
Okay. So if there is any source inductance from the supply, you will be able to explain its effect on the performance of the rectifier. Okay. Number 6 is that we will be able to describe harmonics component using Fourier series. So, input current output voltage. Is there anyone who is writing also with me?
Sir?
Is there anyone from you who is also writing in his notebook or khata? No.
Maybe there are some.
Okay, these are the basic 6 points. After the end of the chapter, you should be able to explain and do all these things. Okay. Now, I'm going to describe some of the things like there will be some symbols that will be used here. Like if it is say ID, if you say average, then you have to understand that this is diode current. D stands for the diode. Average value of the diode. Average and this. That's a diode. So since the first letter in the capital also suffix of capital, it should be average, okay? And also RMS value can be represented here. So then RMS, you have to mention RMS, or in this book it is mentioned the RMS value of the current. And this one IO average means out the average value of the output current. O stands for output, average value of the output current. And also similarly, you can write down RMS, that will be your root mean square value of the RMS value of the output. And likewise, are you familiar with this figure?
Yes, sir. Transformer.
Yes.
Transformer, okay. So this side will be known as the primary side. And this is your secondary side. So usually it is mentioned EP is the primary voltage as ES is the secondary. Okay. So if the current here mentioned like this one, primary current, of course that will be your RMS. And this is if it is mentioned that IS, that will be your RMS current. Okay.
Okay, sir.
And then there will be
mention করে না থাকলে আরএমএস করব
mention করা না থাকলে তোমার ইয়েতে if it is a transformer, then of course the current will be your AC, right?
জি
Then
স্যার
there will be no DC in that. Yes,
Sir.
but you will have to find the RMS value. Yes.
স্যার তাহলে কি স্যার মানে হচ্ছে আমরা যখন ট্রান্সফরমারের কারেন্ট গুলোর কথা চিন্তা করব তখন হচ্ছে যে কোনো কিছু ভালো না থাকলে আরএমএস ধরে নিব আর হচ্ছে ডায়োডের বেলা হচ্ছে এভারেজ
You speak in English. You have some international student. Please speak in English.
Sir, I'm saying that for the transformer case, we will consider like the primary current and secondary current as
All the RMS value,
RMS, if not mentioned.
Yes, RMS value or instantaneous value.
And sir, for the diode case, in the ID, we will assume that it is average value.
ID diode current, if it is mentioned average, if it is mentioned RMS, it is RMS. These are the
okay.
diode current, right?
Sir, if nothing is mentioned,
Nothing mentioned means, okay, if this one not mentioned like this,
yes, sir, I'm asking that.
it will be average. It will be average. Of course, it will be average.
Okay, sir.
Okay, don't get confused. Okay, so PDC will be your output DC power, output DC power. So okay, if it is a rectifier, you know the rectifier is one kind of energy converter, power converter, right? AC
Yes.
side is converting to DC. So the output side will be your DC. So here, if the average value of the output current will be say IO average or IDC, if the voltage is VO average or VDC, then your PDC, the output DC power will be termed as VO DC. Of course, DC multiplied by IDC. So there will be the AC power. So AC power will be your output power. You see, this is the output power. How in the rectifier, how the AC power is coming into the factor. Because sometimes you may not get like this one. This is say V0 and this is your say time T. So this is a DC voltage, right? Is it not? Am I correct or not?
Sir, can you repeat again, sir?
So this voltage I am showing here with respect to time T. It is parallel to your T axis. Is it not the DC voltage?
Yes, sir.
Yes, sir.
Okay. What will be the RMS value of this one? Suppose this is your T. Suppose this is your 2T. Suppose this is your say 100 volt. What will be the RMS value? Same.
It should be RMS. The RMS value should be same.
Same. Okay. And but if it is not like this, suppose you have a AC and DC component here. So if suppose this is your say your T, and this is of respect to T, we can separate the DC component and AC component. This is your AC component, purely AC component, and this is the DC component. And if these two are adding, if you two add, by adding this two, you will get this one. Am I correct or not?
Yes, sir.
So this is also DC, but it has a then we can find out the RMS value of this one, RMS value of this one, and we can find out the RMS value of the current. Then output of the AC power, they call it this is the AC power, that is known as the it will be your V0 RMS and IO RMS. We'll come back all these things later. There will be some other factors we shall define in the correct stage, subsequent stage. Okay. In the last two sections, I have gone with the book, and just on the book I was marking like what your Shagos sir did in your second semester, right? Your second year. He was using the PDF, and on the PDF he was writing. And also I did in the last few classes, I did that. So now I have decided to use this white book and writing. Which one is better for you?
Sir, it would be better like if sometimes you go to the book and then explain.
It is like then I have to share and go back this way, right?
Yes, sir.
Okay, anyway.
Yes, sir, you can use both.
Which one is convenient for you? Because what I am doing, I have the book in another laptop, and from there I am just writing. You understand?
Yes.
So if you think that if I just teach you from the book in the PDF file, then I can do that. Well, which one you prefer?
Sir, I think
If
that
there's a
the
need
combination of book and PDF would be much more convenient for a complete understanding.
Yes, sir.
Okay.
There's a need to explain more, then you can come to the whiteboard.
Okay. The rectifier actually is a circuit that converts AC to DC. Actually, if I write this thing, then you get some time to get your brain active to consume the things. You understand? But if I use the book, you may not get the time. So, okay. So this is nothing but a converter. It converts the AC to DC. A rectifier can be classified depending on the input voltage. If it is single phase, if the input voltage is single phase, then it is known as a single phase rectifier. If the input voltage is three phase, that will be a three phase rectifier. So both of the rectifier we will discuss in this course. Single phase means, okay, if you already, I hope you have already learned this from your power system. So this is the Y connected side of the three phase transformer. Suppose this is A, phase is B, and this is C. If we connect from here the rectifier here, and if we take this output here, so this is single phase, right? You understand?
Yes, sir.
We
Yes,
have
sir.
taken the single phase line, then it will be single phase rectifier. But if you take sorry. Okay, if you take the let me erase this one. If you take the three phase voltage here, the rectifier and all, you will get only the DC here, that will be three phase rectifier. You got my point?
Yes, sir.
Okay. And
স্যার
then
এই যে
also,
আপনি কি বললেন শুনতে পারিনি
if you
Okay.
use the three phase line as the input, then it will be three phase rectifier.
ও
And your output will be DC. And if you take single phase, that your single phase rectifier, circuit will be also defined. Okay.
Yes,
Circuit will be also defined. Now also, depending on the number of diodes you are using, you will have another classification that are like center tap rectifiers with center tap transformer, and also rectifiers with bridge rectifier. So in your second semester, I have taught you this both rectifier with center tap transformer and also bridge rectifier. That load we have used only the resistive, but here inshallah we shall use RL load or highly inductive load. Okay. Okay.
yes sir
Yes, sir.
Now we shall study some of the performance characteristics. This is your 3.2 of your book, performance parameters. I should say. What does it mean by the performance parameter? So what is the performances of Mushfiqur Rahim in the last two matches of the cricket? How did he do? Did you watch the cricket? Is there anyone who has watched the last cricket match between Bangladesh and Sri Lanka?
Yes, sir.
How Mushfiqur Rahim did?
So he was excellent.
স্যার ভালো
Excellent.
খেলেছে
He was
Okay.
man of the match.
So how do you know what is his performance parameters then? How do you-
He
how-
scored 124 runs.
Yes, 124 or 125, and in the first match he also scored around 85 or something.
Yes, sir.
So then the performance is his run rate, right?
Yes, sir.
So this is his performance parameters, and also in rectifier we have some of the parameters we can find out. One is the known as the rectification ratio. Rectification ratio. Sometimes people call it efficiency also. The rectification ratio will be termed as PDC by PSC. Okay. So So what is PDC then? It is the VDC means the output voltage of your, if it is rectified. So AC is coming from here, single phase we are showing, and also this is your VDC. And if it is output voltage V0, you have to find out the VDC average value. Also, you have to find out the IDC average value of the current, then that will be PDC will be your VDC multiplied by IDC. Okay.
Yes, sir.
This is your this equation is 3.1 of your book. And RMS value of the output voltage, as I mentioned, that if it is non-sinusoidal like this, you can find out the RMS value of the output voltage. That is your this is your RMS value of the output voltage. This is the RMS value of the output current. Output voltage RMS value, and this is output current. Then your TAC will be defined as VRMS multiplied by
IRMS.
RMS. So look here, in your book they did not mention the O, but if it is VRMS RMS, you have to understand this is your output. It is coming, but in my opinion, it could be also in your input. Anyway,
Sir, can you clear that O part again?
They did that, although they are mentioning in your book it is output, they did not mention. Put the O. They'll just write down VRMS RMS. And in my opinion, this should be also the input RMS, and that should be the, if it is a lossless, there will be no drop in your rectifier. So this VRMS and IRMS is the same as you are also in the input side. Okay.
Okay,
Anyway,
sir.
don't get confused. So this is the rectification ratio. We have to find out for this center cut transformer based rectifier or bridge rectifier. We'll go to that one very quickly. Okay, now this is your equation number 3.3 and 3.3 and 3.2. Equation number 3.2 is like they write down PAC equal to VRMS IRMS. Okay. Oh,
Yes, sir.
now I'm going to tell you some of the things. As I mentioned you, if you have an output voltage like this, V0, and if it's time t, then we can always. So this is the DC component is here. This is your DC component. This is your VDC, and this AC component we can always write down this way, right? This is your AC component. So how can we find out the RMS value of this from there? From there, how can we find out the RMS value of this AC? You don't need to do all these things. You have to find out the say peak value, and then you get the equation, and then you do your integration, squaring it and averaging it, and then you do that will be PR. So you can find out the effective value of the AC component of the output voltage. That means here, effective means RMS, right? You know that. Do you know it? Effective means also RMS. So you want to find out the only the RMS value of the AC component. That will be termed as VAC, and the formula is you can find out here, but I am not doing this one. That should be given in your chapter 2 of NetBond. If you want to go, and you just go and see. This is your equation number 3.4. So what is this RMS?
The RMS value of the AC wave shape.
This is the RMS value of the total wave shape, not the AC, total.
Oh, okay. Yes, sir.
And this DC is the nothing but the this DC value, okay? You square the RMS value of this one, and then you negate the DC value, square of the DC value, and take the root over that will give you the only the effective value, or only on the AC component. Only the AC component that we need to calculate to find out some of the things. What is that? There is a factor known as form factor. This is form factor. It is defined as VRMS by VDC. So you know that, yeah, you can find out the VRMS. If you know the, say, equation of this one, then you can find out the VRMS. And then you have to find out the VDC. Or you can use the Fourier series analysis to do that, but we don't need to do it. So this form factor is defined as VRMS by VDC. And this is the equation of 3.5. And there is another factor. This is known as the ripple factor. Ripple factor. Sometimes people call RF. This is VRMS by VDC. Oh, sorry. VAC. VAC by VDC. What is this VDC? The effective value of the only the AC component, okay? And that has already, we have defined
VRMS square minus VDC square.
Then if we put this one, the ripple factor will be a VRMS square minus VDC square divided by VDC square under the bracket, and that will be your form factor square minus 1. That will be also your equation number. This one is equation number 3.5 of your book, and this is your 3.7 of your book. Okay, so now I'm going to define this one. I have already given you the derivation in your messenger. Did you see it? Transformer utilization factor. Transformer utilization factor. So that is defined as PDC by actually rating of the transformer in volt ampere transformer, and that is your PDC, and this is the secondary RMS value and secondary RMS current. And with that one, for the center plate transformer, I have already derived the transformer utilization factor, and I have posted in your messenger group. Did you get it?
Sir, checking, sir.
Hey, so you don't see it?
Oh, yes, sir. Yes, sir. I have seen it now, sir.
And also, the input power is nothing but the VSIS, the input power factor. The input power factor will be P in, sometimes people call PSC, and divided by VSIS. Okay. So these are, and there will be another factor, last one I am defining. This is equation number 3.9, and 3.10 is the test factor. Are you familiar with this test factor?
No, sir.
Peak value of the secondary current, and also the RMS value of the secondary current. If you take the ratio, that will be known as. So these are the things that will tell you how your transformer is. What is your what is the performance? Giving you by now. Well, we should start two type of single phase now. One is the center transformer and another is the bridge rectifier. Initially, we are reviewing the thing that we have already covered in second semester, where we have forgotten. Let us do that thing first. So I'm doing the single phase full wave rectifier. Single phase full wave rectifier. First, because we shall discuss that. And let us start from the center. One is the center tapped transformer based single phase rectifier. Okay, if you remember this thing, we have already done here. So that this will be your actually primary voltage, and this will be your secondary. This side is the secondary. Okay. So if we take the turn ratio 1:2, then N1 by, are you familiar with N1 and N2?
Yes,
Yes,
sir.
sir.
Trans ratio.
Turn ratio. So then S prime. So Vp by S prime will be your
N2 by N1.
N2 by N1 by N.
N1.
Yes, sir. Yes, sir.
Okay, so then your Vs will be double of your Vp, right?
Yes, sir.
And then Vs prime is a double of. Then in the center of the winding, we are taking a tap, and then let us put a load here, and we should use a diode here. We should put another diode here. Then that will be your Vs, and this is your Vs. Then Vs prime will be actually nothing but 2 Vs. You understand it?
Yes, sir.
Yes, sir.
Okay. So this Vs we shall use that Vm sine of omega t. Is it clear
Yes,
Yes,
sir.
sir.
so far? Okay. As someone mentioned that we can always go to use the book sometimes. Let us use the book also. So far I have covered all these things. The first one, all these things I have covered. Okay. Now, here they have mentioned this figure, and I have also done this one. So this is your input voltage. This is your input voltage. Up to this one positive or negative?
Positive.
Positive. And then after pi it is going negative peak, right? What will be the equation of this if it is Vs? What will be the equation of this one?
Vs sin
Vm
omega
sin
t.
omega t.
Vm sine of omega t. Okay, so if you don't know Vm, but rather than if you know Vs, that is the RMS value, then what is the relation between your Vm and Vs?
Vs equals to Vm by root 2.
That means Vm equal to root 2 by Vs, right?
Yes, sir.
Do it multiplied by Vs. So then you can always say root 2 Vs sine of omega t. Can you see that thing? Can you see this area also?
Yes, sir.
Okay. So now,
স্যার এটা
here,
একটু আরেকবার বলবেন যে VS RMS value agent.
Do you know this relation?
Yes,
Peak
sir.
value is √2 multiplied by Vs, where Vs is the RMS value and Vm is the peak value or maximum value.
Yes, sir.
So, okay, so just I have insert this one. Vm equal to √2
Okay, sir.
Vs. That I have done. Okay.
Yes, sir.
Okay. Now, when this voltage is positive in your input, look here. When the primary side is positive, that means primary side you are getting a voltage positive. Also from here to here it will be positive. Here to here it will be positive, right? So this negative voltage, what will happen to this diode? It will be forward bias or reverse bias? For the positive of your input. Tell me, T2 is conducting or not?
Sir, positive time conducting হচ্ছে.
Which one is conducting, D1 or D2? This is positive.
Sir, D1.
D1, and this one is not conducting, right?
Yes, sir.
It is reverse bias. So I can say here D1 is conducting, D1 is conducting, and D2 is off.
Yes, sir.
So if it is conducting, if this diode is ideal, what will be the voltage across it?
It will be short circuited.
Short circuit. Okay. Then if this one is open, the current is going this way, the current is going this way. What will be your VO with respect to across your resistance after your custom?
Yes.
Yes.
So you're getting this one, right?
Yes, sir.
And current is going this way. So you are getting V0 is equal to Vs, and also I0, we can write down I0 up, right?
Yes, sir.
Yes, sir.
What will be the voltage across your D2 diode, second diode?
It will be open circuit. So in
Then you apply your Kirchhoff voltage law. VD2 will be your minus 2 Vs when omega t equal to 0 to 5. Apply Kirchhoff voltage law. This is your negative, positive, negative, positive, negative, positive, 0, right? So VD2 will be minus 2 Vs. You understand? You apply the Kirchhoff voltage law this way.
So the whole loop.
Whole loop, yes. So
Yes.
the voltage across the VD2 will be, look here, minus, this will be the peak value, so minus 2 Vm. So now the diode D2, these are the concept. When diode D2 is not conducting, what will be the peak inverse voltage? Are you familiar with
Minus 2
PIV?
Vm.
Minus 2 Vm, right? That means the peak value of the whole winding voltage, right? In the negative.
Yes, sir.
Yes, sir.
So this diode must withstand this voltage in the blocking mode. You understand what I mean? Suppose this
Sir.
is V, and suppose this is your I, diode voltage diode. And when this D2 is not conducting, suppose it is not conducting, current is 0, current is 0. So this voltage minus 2 Vm has already, even at the peak inverse voltage, this point. So as omega t equal to pi by 2, your D2 got this minus 2 here. I am correct or not? You
Yes,
understand what I said?
Yes, sir.
When the input voltage is positive, then your D2 is not conducting, and we see that the voltage across it is equal to minus 2 Vs. Then peak value will be minus 2 Vm, minus
Yes, sir.
2 Vm. So this value, okay, if we go here, we see that it has got this minus 2 Vm voltage as omega t equal to pi by 2. This is pi by 2. this point. Am I correct or not?
Yes, sir.
Now, if your breakdown voltage is here, then what will happen?
It will conduct.
So in the diode, when a diode is off, ideally we don't want the diode to conduct, right?
Yes,
Sorry,
sir.
off. When the diode is off, when the diode is reverse bias, we don't want to break it down. So when you will go to market and buy any diode for your rectifier, so you have to design your circuit and ask the seller that my PIV should be greater than 2 VM. So he will not understand what is VM. You have to tell, okay, if VS equal to 100 volt, what will be your VM? If VS equal to 100 volt, what is your VM?
√2 into 100.
Then
No,
141,
I
right?
have it.
141 volt, right?
Yes, sir.
Then what will be your peak inverse voltage of your diode?
2 into 141, which is
That
like
means
282.
282 volt, right?
Yes, sir.
Then you have to go to market and ask them, so give me a diode whose PIV must be greater than 282, maybe 400 volt. If you buy any diode whose PIV is equal to less than 282, then your rectifier will not work. Because when D2 will be in the reverse bias at omega t equal to pi by 2, you will see that it will go to the breakdown and current will flow in the reverse direction. When the diode will be reversed or any device will be reverse bias or off, the ideal characteristic we have learned from chapter 1 that there should not be any current flow through this diode. You understand what I say?
Yes, sir.
Okay, now when you're in, okay, I'm taking all things out again. When your input voltage is, this voltage VP is negative and here like this, then it has changed its direction here also. This is negative, this is positive, this is negative, and this is positive, right? So what will be the biasing condition of this here?
So reverse bias.
So it will not work, right?
Yes.
And then current will flow this way. So we have already found V0 is equal to IOR, and current was flowing this one. Still now current is flowing this way, right?
Yes, sir.
So we'll have to get the same wave shape. That is why we are getting whatever we got here, we'll get the same here. And what will be the wave shape of the voltage of your T1? Like VD1 in say pi omega t by twice pi. What will be VD1? Can anyone tell me? You apply the Kirchhoff voltage law, you will say that minus 2 Vs. Am I correct or not?
Yes, sir.
Yes, sir.
Then its peak inverse voltage of D1 is also minus 2 Vm.
Yes, sir.
Here it is mentioned here. Look here, it is mentioned here. VD1, this is the voltage of the VD1 and VD2 is equal to 0. This is your wave shape of VD2 and the VD1 is 0. You got my point.
Yes, sir.
Okay, now if you want to take the average value of this one, what will be the average value? What will be the average value of the full wave rectifier? VDC, the average. We have to, okay, Vm square sin square omega t. RMS means square, mean, root. So first you square it, then take the mean. So since it is repeating, we can take up to 1 pi. So 0 to pi, and then 1 by pi, and take the root here, and you will come as 2 Vm by pi.
The reason that average voltage expression 2 by pi into Vm. So 2 by pi into Vm, isn't that the expression for the average?
Yeah, then 2
2 by
Vm
pi into, yes, sir, yes,
yes,
sir.
yes, yes. Yeah, that we have got. if you do that, it will come 6.636 VM, right?
Yes, sir.
Sixth, if you replace VM by √2 VS, where VS is the RMS value, you will see that it is 0.9 VS. So if your RMS value is equal to 200 volt, what will be your average value of two-wave rectifier? If your RMS value is equal to 200 volt, what will be your VDC?
0.9 into 2.
0.9 multiplied by 200. Do you need calculator?
180.
184. Okay, for the half wave rectifier, what will be for the half wave rectifier? What will be VDC with respect to VS then? 0.45 VS, okay?
Yes, sir.
Because you will not get this part.
Yes, sir.
This part will not be available. You will only get this one, and the negative side here will not be there. Then, since you are getting only half, and the average value will be half of your today, you have to remember for your quiz all these things. Okay. Let us go to discuss the bridge rectifier. You want me to use the now the whiteboard?
স্যার গ্রাফ আছে তো এখানেই থাকি গ্রাফ
Okay. So bridge rectifier we have already discussed earlier. You may not use the transformer here because you don't need. But in the center tap transformer, you must center tap based rectifier. You must need the transformer. You can directly give this one to the supply directly. You don't need this one. But then you are working with the line voltage and line frequency also. Okay, I forgot to mention here. Since we are taking the voltage from the line, it will be also known as the line frequency rectifier. Okay.
Yes, sir. Yes, sir.
Okay, now. So we have in the second semester, if you remember that, okay, it is like this. Let us use the transformer because transformer sometimes used to step down the voltage and also to isolate the input from your rectifier circuit.
Sir.
Okay, so now if it is positive, this diode must be conducting, and then this is your resistance, that means your load is 0 and then your I0, and we must go back to any diode, and you can this diode, this D1 and D2 will be working for the positive half second. This is nothing but this D1. Look here, the positive supply is connected here, and that has gone to the load, and that has gone to the load, and the negative part of the load, that means this one is connected to the anode of the diode, and it has come back to the transformer. Is it okay? Is it okay? So this part is the replica of this one. This one we have already done that thing in your second semester. And for when this what is negative and this is positive, that means then there should be a diode here. This is known as D3, and the current is going the same way, and it should go back here. This is your D4. So did we do that thing in your second semester? This bridge rectifier. Hey, you are not saying anything.
স্যার মনে নাই মনে পড়ছে
Okay.
Yes, sir. We learned it, sir.
You have learned. I taught you. So this is nothing but replica of these D3 and D4. So forget about this thing. From nowadays, we will draw the rectifier, this rectifier like this. Okay. So that will be a D1, this will be D2, this will be a D3, and this will be D4. This way, you have to number your die, D1, D2, D3, D4. And then you have to connect the input like this. This will be your input. And your load will be connected here. This is what type of rectifier this one? Which one is this one? What type of rectifier?
Bridge rectifier.
Bridge rectifier. Okay, now let us discuss the wave shape, how it works. When the voltage is positive, that means here, which diode should be conducting? Tell me by looking at your figure. You tell me which diode should be conducting.
So D1 should be conducting and D2 should be conducting.
Yes, D1 and D2. So now here, D1 and D2 should be conducting, and D3 and D4 will not conduct, right? It is open. So
Yes.
if the voltage is this VD3 or this is your say VD4, okay, when the D1 and D2 is conducting, what should be the voltage across D1 and D2?
So 0.
0. And when D3 and D4 is not conducting, what should be the voltage across your VD3?
Infinity. Not conducting, sir.
So you have to apply the Kirchhoff voltage law. Okay. I'm drawing, okay? So this one, D1 is conducting, and this is your resistance, and then you open, and then D2 is conducting. And that is also connected here. And this is not conducted. So this will be your VD3. Oh, sorry. This is your VD3. So this is your VS. Now you apply your Kirchhoff voltage law and try to find out.
Yes.
Tell me.
So VD3, it should be VS, sir.
It should be VS, right? You can check. It should be VS because this is shorted and this is also shorted. Now you apply negative positive, then you go there, negative positive VS, and then negative positive VD3, then you complete here, right? You have already gone here. So start from here and gone here, you will see that VD3 is nothing but the minus VS. You understand? You apply the Kirchhoff voltage law. Don't get confused, man. Negative positive, negative positive, then go, then negative positive, and you are coming back here. So you have already completed the equation, and it is VD3 is equal to minus VS. That it is coming. Look here, VD3 and VD4. So what is the peak inverse voltage for the diode D3 and D4 when the diode is not conducting?
Yes, sir.
When diode D3 and D4 is not conducting, what is the peak inverse voltage across that diode D3 or D4?
Minus VS.
Minus VS means peak inverse. I am talking about the peak.
Oh, so minus VM, sir.
So look here, we are getting minus V. So it is the difference between the your center tap and this one. In the center tap, whole winding voltage is here, and this is 2 VS, but here we are getting single VS. Okay, and we are using here 4 diodes. There we have used 2 diodes. Okay, now if you apply the Kirchhoff voltage law, you will see that V0 will be nothing but VS. Apply negative positive and then positive negative. And since the current is going always the same direction, so in the negative half cycle, when this diode will be conducting, this diode will be conducting, this will not be conducting. We'll get also the same thing, like that we get here. And this is the voltage across your diode when it is D1 and D2. In the negative half cycle, they are not conducting, so the VD1 will be or VD2 will be a minus V6. I hope you understood.
Yes, sir.
Yes or not? These are very simple things we have already covered in your second semester. You forgot everything. This corona has done a lot of. Okay, so this is nicely given, and this is the table that has been given. What are the advantages that is the center of the transformer? We have that simple only 2 diodes, limited low power supply. Actually, these rectifiers are used for the low power supply, maybe less than 100 watt. Ripple frequency is twice the supply frequency and provides an electrical isolation. Since we are using the transformer, this input side is isolated from the output side. Disadvantage, increased cost due to the center of the transformer. Bridge rectifier suitable for industrial application up to 100 kilowatt. It is up to 100 watt. 100. Ripple frequency same as you understand what does it mean by ripple frequency? In your input here, it completes the 1 cycle. Here you are completing 2 cycles. Same thing, right? That is why frequency will be double of your input frequency. You got my point?
Yes, sir.
And simple
Sir.
to use in commercially. Okay.
Sir, if we use, if we use these rectifiers, we are actually using for DC output, right? But sir,
Yes.
if we get the ripple, sir, isn't it actually bad for our electrical devices?
Of course, you will have to use the rectifier. Sorry, filter,
Capacitors.
capacitor, yeah, mainly capacitor. This capacitor will give you like this. Also inductor and capacitor, low pass filter. Okay.
Yes, sir.
Okay, so commercially available units, like if you go to market and ask them, okay, give me rectifier of this rating, they will give you like one IC type things. So you can buy it very cheap. And although input side transformer is not needed for the operation of the rectifier, one is normally connected to isolate the load electrically from the supply. For the bridge rectifier, actually we don't need the transformer, but you can use this one to isolate the input side from your rectifier. Okay?
Okay, sir. Sir,
Yes.
I have another question, sir. If
Go ahead.
ripple is actually bad, then sir, why is it actually written in advantages?
Where?
I mean, in the advantage, like ripple frequency is twice the supply frequency.
Mhm.
But what is the advantage actually?
Actually, it is not an advantage. It is that, okay, advantage is that actually it should not. It should not be advantage. Rather than it is a characteristics, I should. So actually, the thing is that if we have like this, only one of this one, and in the negative cycle we don't have anything. But it is better if you have like this, the double frequency. If you have the triple frequency, that will be better. If you have the multiple frequency, even that is best. You understand what I say?
Yes, sir.
This in that point, you can say double frequency is an advantage rather than the single frequency what we got for the half wave. Okay?
Okay, sir.
That I understand. Actually, I am not also very much convinced why they have put like this. Okay. Just a minute. Just a minute. Now, these are the 3.1. I have already. So you study very hard for this one because I may set some problem from here in the quiz. So VDC is 2 Vm by pi, and it is coming in this one. IDC, this is the resistive load they have used. So VDC by R. And then VRMS. VRMS will be same as Vm by root 2. You don't need to integrate this one. We know that, right? Because, okay, this is your sinusoidal input, right? When you find this, suppose this is your Vm, what will be the RMS value?
Vm by root 2.
Yes, Vs, we call it Vm by root 2, right? Because when you are squaring it, when you are squaring it, then it will coming like this. Am I correct or not?
Yes, sir.
Yes.
And then you are taking the mean and then root. So in the output side, we are getting this one already. So if you are squaring it, we will get the same thing as this one, right? So that is why your RMS value will be the same of your sinusoidal. RMS value of the output voltage will be the same of your sinusoidal. You understand it? What I say?
Yes, sir.
Then RMS current will be nothing but the VRMS by R. Now, if you use all the formula, then to find out the different performance parameters, then suppose first one you can find out what will be the rectification ratio of efficiency. That should be VDC by PS. So you already know, you have already found this one and this one. Yeah, then your VRMS, IRMS. And if you do that, then you will find out that will be your 81%. Okay, and then form factor. Form factor, the formula was, what will be the formula of the form factor? Can I tell me form factor? VRMS.
VRMS by VDC.
VDC, right? So we already know that VRMS equal to 0.707 Vm and VDC equal to 0.636 Vm. So it is 1.1.
1.1.
Okay.
Yes.
And then and this for ripple factor will be form factor square minus 1. That is this one. And this is for 48.2. And then the transformer utilization, I don't know how they get this one. That is why I have already given you the derivation of the transformer utilization ratio. You use my derivation, what I have already posted in the messenger. Okay?
Okay, sir.
Okay, the peak in reverse voltage, 2 Vm, we know that. So that is this one, and the ripple factor will be peak current of the RMS value, peak value of this secondary current. That means your Vm by R, and Is will be this is nothing but 0.707 means that RMS value, and you got this one, and if you use this formula, then you will get root 2. And input power factor, I have already defined this one. So PSC by VA. So PSC we have already found VDC VRMS multiplied by IRMS, and VA is VRMS IRMS, and finally we get it will be 1. So this is the problem. So you also note this one. Transformer utilization factor is 1 by the signifies the input transformer is present must 1.5 times larger than that when it is used to deliver power from a pure sinusoidal voltage. The rectifier has a ripple factor 48.2 and rectification efficiency 81%. What does it mean? All these things you think and report me. Okay? Inshallah.
Okay.
So what is the time? Almost finished, right?
Yes, sir. 5
Yes,
minutes remaining.
But you came 10 minutes late. Anyway, so I have covered until this one from your so what should I say? From section C and A. I have covered. Oh no, I have also tell them this one. Just quickly, let me tell you. So if the rectifier has a voltage like this, and you know the Fourier series, right? This is your output voltage is pi, and this is your twice pi, and suppose this is P, and you can use the Fourier series analysis here. And you know the VDC. VDC will be the same as before, what we have already done, what 2Vm by pi. And this AN we can find out. The formula of the AN is this one, ultimate this one, and it will be 0 for N. If you put N equal to 1, 3, 5, that means the odd harmonics, it will be 0. And for the even harmonics, you will get this expression. And Bn will be always 0. Finally, you will get, if you put this one here, then you will get V0 will be your 2 Vm by pi, sorry, 2 Vm by pi. This is the DC value here. And then you have to use this one for n equal to 2, say 4 Vm by pi. Then if you put the minus 1, 2 minus 1, 1 and 3, that means 3. That means there is a negative here. So 3 pi cosine of 2 omega t, n equal to 2. You understand what I say? You have to just V0 t, we have to put VDC plus AN n omega t n equal to 2, 4, 6 up to infinity. And then what is AN? For 2, 4, AN has already been given here. For you, we have calculated it 4 Vm by pi. Then equal to 2, 4, 6 infinity minus 1, n minus 1, n plus 1. So suppose you are putting n equal to 2. So what will be 8? 4 Vm by pi, then minus n 2 minus 1
Minus
is
1 by 3.
1 by 3. So that, and then it will be your cosine cosine n omega t. So now your VDC will be 2 Vm by pi, and then for the second harmonics we will get what? 4 minus 4 Vm by pi 3 cosine of 2 omega t. And then for the fourth harmonics you have to put n equal to 4 here. You got my point?
Yes,
Yes,
sir.
sir.
That will be your 4 Vm by 15 pi cosine. So if I ask you what will be the peak value of the second harmonics, then what will be your answer?
Peak value of the
Second harmonic component. This one. This will be the peak value of the fourth harmonic component. This will be the peak value of the sixth harmonic component. You understand?
yes, sir.
If I ask you what would be the peak value of the third harmonics? What will be the peak value of the third harmonics? For this type of wave?
4 Vm by 15 pi.
No, for you see, for the odd harmonics, AN and BN, both are 0. Odd harmonics means 3, 5, 7, 9. You got my point?
Yes, sir.
Yes.
This is 0, and BN, this is also 0. So you have only the DC value. So you don't have any third harmonics, fifth harmonics, seventh harmonics. You have only the even harmonics. You understand what I say?
Yes, sir.
Yes,
Sir,
sir.
I thought that from the 3.12 equation, the third term.
So if quizzes, if I ask you for full wave rectifier, the peak value of 15th harmonics, 1, 0, 2, 1 by 15, 3. 1 by 2 into 15, 4. 1 by 3 into 3. What will be the answer?
0.
This will be answer. And for the second harmonic, this one. For the fourth harmonic, this one. For the sixth harmonic, this one. You have to remember, okay? Is it okay?
Yes, sir.
Yes, sir.
Okay, now I am going back and taking your attendance. Hold on for